Hi everyone, this is a combined lecture for both Physics 112 and Physics 102. This is for Physics 112. This is the March 18th lecture. It's part two. Part one was a, short little review on oscillators, and you should have viewed that before this one. For Physics 102, this is the March 19th lecture. Your previous lecture was the March 17th lecture, which was on the review on the wave equation. Okay, and so you can see here I'm just going to start directly on our website, freeskies.net, and we're going to log in. And I'll show you where these notes are. So because this is a combined lecture for both 102 and 112, in 102, if you click here, and you scroll all the way to the bottom to our online lectures. This is the March 20th. Okay, this is the March 20th lecture. For the Physics 112, this is, if you scroll all the way to the bottom, this is again March 19th, but it's part two. Both are identical, so we can take a look at either one of these. And so let's start off here, and let me actually just slightly shrink my image here so we can see. Maybe move myself down here. Now let's move back up there. Sorry about that. All right. And let's take a look. This lecture is going to be on waves. We're going to not so much look at the theory of waves for Physics 102. That was the lecture on wave equations. Rather, we're just going to look at some wave phenomena that are provable out of the wave equation. Okay, and for Physics 112, well, this is the beginning of our introduction to waves. Okay, so what we have here is basically you can think of this as a wave on a string, and you can see there's a line, the x-axis, and that's basically the equilibrium of this string. If you didn't disturb the string, it would just be a straight line with some tension. But if we grab one end of the string and we start to wiggle it, what you're going to do is you're going to get a wave going in that string, and you can see there that's the sinusoidal wave pattern. Okay, so what things should you notice about this? Well, first thing you'll notice is that the entire wave pattern moves in this particular diagram moves to the right at some constant velocity v. Okay, so when waves move, they don't speed up, they don't slow down, they don't accelerate or anything like that. They just simply travel at a constant velocity. All right, and so if you were surfing at the top of any one of the crests, you would simply be moving to the right at a constant velocity. However, that's not the motion of any particular particle in the wave. Okay, the entire wave itself can be thought of as a set of oscillators, and so you could see over here I have this you can see over here I have this point, and you can say, well, what's the motion of that point? If you had a string and you put a little dot on that string and you watched it, that point in the string would just oscillate up and down, up and down, up and down like that. Okay, and so any point in the string just acts as an oscillator, but as a collective phenomenon, the entire wave pattern retains its form and just moves in one direction at a constant velocity. Okay, so one of the properties of waves is the velocity, and it is constant for a particular wave. Okay, another property of waves is the wavelength, and you can see it there marked as lambda. Okay, and lambda is basically the distance from one crest to a neighboring crest. Okay, you can measure crest to crest, you can measure trough to trough, or from any point in the wave to a similar point in the wave. For instance, like here where you're crossing where the string crosses the equilibrium, and then over here where the string also crosses equilibrium. Okay, and that distance is lambda, and that distance also doesn't change as the wave propagates. Now, if you created a different wave in the same material by, say, wiggling the string faster or slower, then you can create waves of different lambdas. But once a wave has been created with a particular lambda, it just continues with that lambda and it moves along. And so that's the second property of waves. There's the velocity, there's the wavelength, and then a third property of waves is the frequency. And you can see here I've got this this image here. It's supposed to be like an eye viewing a particular point in the wave. So you're just going to observe that point in the wave, and you ask the question, how many crests travel past this point per second? And the number of crests that pass that point per second, that is known as the frequency. Okay, so again, you could be looking at the number of crests that pass a point per second, or the number of troughs, or any number of points of similar phase. Okay, so you just say how many of these points travel past per second. That's your frequency, okay? And so that's the third property of waves. There's also the amplitude, which you see over here, but for now we don't need the amplitude. It turns out that the other three are related to one another, but the amplitude is not, okay? We will come back to the amplitude in the next lecture because the amplitude is going to be related to the intensity of a wave, and the intensity is just how loud a wave is, so like sound. Okay, we're going to talk about the intensity of sound, and that comes directly out of the amplitude, but we don't need that right now. Okay, so I just have that described down here. Velocity, okay, again lambda is the other one, and then frequency. Okay, now these three properties, lambda, f, and v, they are not independent of one another. Okay, they have to be such that if you multiply lambda times f, that's equal to v. Okay, for physics 102, that came out of the wave equation. But you can easily see that because if you take lambda, that's the distance traveled by a crest, divided by a time it takes to travel that, which is capital T. Lambda over capital T is your velocity. Now you don't see capital T there, but the frequency is just the reciprocal of the period. And so lambda times f is the same as lambda divided by capital T. Distance traveled, time it takes to travel that distance. Well, that's a velocity by definition. Okay, so this velocity of the wave doesn't change. Okay, you can create in a particular medium, like in a particular string with a particular tension on it, you can create waves of different wavelength and different frequencies. Okay, but all of those waves are going to travel with the same velocity. All right, so basically the speed of waves in a particular medium is fixed irrespective of lambda and f. So if you change lambda, you necessarily change f in that equation. You don't change v. All right, so I gave you this equation in class, and there it is again. You can see the second boxed equation near the bottom there. V is equal to the square root of t over mu. That is the speed of waves in a string. Okay, speed of waves in a string. So, and it's actually the subject of our lab next week. So there's a tension in this string, and that's just how much force you're stretching on the string. And there's also a linear mass density, which is given the symbol mu. And what mu is basically if you have a certain length of string, little l, and that's length of string has mass m, then the linear mass density is the mass of the string divided by the length of the string. Okay, it doesn't make sense to talk about the ordinary density because a string is a one-dimensional object, and so you just do mass per unit length rather than mass per unit volume. Okay, so that's why it's called a linear density, not just an ordinary density. All right. Well, this is just a repeat of what I said earlier, that the frequency is 1 over the period. And so, if you want to understand that equation, you can simply look at, think of it as velocity as the distance traveled divided by the time it takes to travel it. Again, the distance you're going to travel, if you wait a time capital T, one crest will travel a distance lambda because it'll travel from where one crest is to where its neighboring crest was a minute ago. And so traveling a distance lambda in time capital T, there's your velocity, lambda over T. And if we usually work in frequency rather than the period, so if you replace the 1 over T by F, you get the formula that we just saw, V, which is equal to lambda F. Okay. All right, so this is a problem we did in class. I'll just go over it very quickly here. We have a guitar string, and it's 3 meters long, and it has a mass of 15 grams. Okay, we force one end of the string to vibrate at 250 hertz. That is, we bob it up and down 250 times per second. Okay, and we put the string under a tension of 1,000 newtons. And I want you to find the wavelength. All right, so there's quite a bit going on here, but realize that the wavelength that we want to find is related to this the velocity because of the frequency, because lambda times f is equal to v. And you say, well, if only I could find v, but you can, because you can see here that v is basically equal to the square root of t over mu. The tension I gave you is 1,000 newtons. Mu, I didn't give it to you directly, but 3 meters of this string has mass 15 grams. So if you take 0.015 kilograms divided by 3, that tells you that the linear mass density is 0.005 kilograms per meter. And you substitute that into the square root of t over mu, and you basically get that the velocity is going to be 447 meters per second. Okay, now that's fixed because in part B, I'm actually going to change the frequency. When I change the frequency, or the lambda is going to change, the speed of the waves will not. Okay, and so at this point, we have the velocity, 447 meters per second. I gave you the frequency, and if we use lambda times f is equal to v, we can simply determine that the wavelength has to be 1.79 meters. Okay. Now in part B, I said, well, rather than causing the string to vibrate at 250 oscillations per second, we're going to do 500. Well, then what happens? The velocity doesn't change. So you can see here I'm using the same formula, lambda is v over f. V, I still substitute 447 meters per second. That doesn't change, as we've already stated, but the frequency changes, and as a result of changing the frequency, lambda changes. Okay, and so this time we'll actually get, because we're at a higher frequency, you're actually going to get a shorter wavelength of 0.9 meters. Okay, and so that equation, it's got three variables in it, but one of them being fixed means that there's kind of a reciprocal relationship or inverse relationship between lambda and f. And since v is constant, if you go to high frequencies are going to correspond to short wavelengths, and low frequencies, so when f is low, then you're going to have big lambda or long wavelengths. Okay, so lambda and f are in reciprocal relationship to one another. All right, so that's a quick introduction to waves and how they travel. But there's some. Now we're going to turn to some of the phenomena that waves undergo, and the first one we're going to look at is standing waves. Everything that I told you about so far is just about waves that are traveling on a string, which is really infinitely long. I didn't say anything about like what was happening at the endpoints. I didn't say anything about how we were, causing the string to vibrate or anything like that. We just assumed that the string was already vibrating with a wave in it. But strings or waves are usually bounded by something. Okay, so that means that if you've got like a string on a guitar, you've simply tied it down at two ends. And the vibration, whatever vibration that string does, has to happen in the middle of the string. It can't happen at the two endpoints because you forced it to not vibrate at those two endpoints. Okay, and so when you have that kind of a situation, you're led into what are called standing waves. Okay, they're called standing because they're not. You can't see them traveling to the left and right. Okay, so unlike the previous waves that we talked about, where the entire waveform would move to the left or to the right at a constant velocity, standing waves, they don't seem to be moving. Nonetheless, they still have a velocity associated with them. If you want to think, this is for the Physics 102 people, you could actually think of this as waves that are superimposing on one another. Okay, so when you have these two waves, like two waves that superimpose, they can superimpose in such a way that you have just two nodes as two zeros of the wave at two endpoints. They're like that. So there is still a velocity associated with these waves. But leaving that aside, let's just take a look at what kind of patterns you get. Okay, so if you tie down a length capital L of the string, okay, that's the only length of the string that can actually vibrate. All right, so you can see there that for the first diagram, okay, you've got the very middle of the string vibrating. Okay, that's called the antinode, and then the two endpoints there where it's tied down, it doesn't vibrate there. Those are called the nodes. Since there's just like this kind of this one bubble in the middle where it's vibrating like this one bubble in the middle that's vibrating, we call this one n equals 1. Okay, n equals 1. And if you ask the question, what's the wavelength of that wave? It's not obvious, but it's actually 2 times capital L. And you go, why? Well, because if you take a look, it's just one crest in there. Okay? And one crest is only half a wave. Where's the trough? Well, the trough, if you were to extend this, would be out here somewhere. And so it turns out that lambda is actually 2 times capital L for n equals 1. Okay, for n equals 2, basically you have two antinodes, that is two little bubbles that oscillate like this. They oscillate 180 degrees out of sync, okay, up and down. And so we call that one n equals 2 because there are two antinodes, two areas of large oscillation. And if you ask the question, what is lambda for this? Well, it's pretty obvious. You have exactly one lambda fitting in the distance capital L. Okay, so lambda 2, the little subscript 2 means we're talking about n equals 2. Lambda 2 is exactly equal to L. All right, and this continues. It just continues until the string simply can't sustain any more antinodes. But you could have n equals 3, and for n equals 3, you've got 3 areas that are bobbing up and down there, and there. Okay, and now if you ask what's lambda there, well, it's 2/3 of L, and the reason is by the time you've made one complete cycle, you've only traveled 2/3 of the way across capital L. Okay, and just looking at these three, you can see that a pattern is emerging. Okay, so if you say lambda 1, that's equal to 2L, but you can write that 2L as 2L over 1. You go, why did you do that? Well, because it'll help us to see this pattern. So now you take a look at lambda 2. Lambda 2 can be written as 2L over 2. And lambda 3 can be written as 2L over 3, and so on and so forth. And so you basically get that lambda n can be written as 2L over n, where n is an integer. 1, 2, 3, 4, 5, and so on and so forth. Okay, so when your string is unbounded, it isn't tied down at both ends, any old lambda is allowed in there. Okay, you can have short wavelengths and long wavelengths. But as soon as you tie down the string at 2 points, that boundary condition, what it does is it causes only certain lambdas to be allowed. Okay, so these are only discrete lambdas. Okay, rather than getting the continuum on the unbounded string, you get discrete lambdas, discrete wavelengths on the bounded string. Okay, and this discretization of the wavelength means that there's going to be a corresponding discretization of the frequencies. Okay, and so again, lambda times f equals v, that's still perfectly valid. Okay, even though the wave doesn't seem to be moving to the right or left, there is a velocity associated with it. And so if we have these discrete lambdas, we can use that equation to get our discrete frequencies. Okay, and so over here you can see that I'm working with I lost the capture. 1 second. Okay, over here you can see that I've got f is equal to v over lambda. I just rearranged it. But now, not only old lambda is allowed, but only our discrete lambda n's are allowed. And so we have that a discrete frequency, fn, is going to equal v divided by lambda n. And we can simply substitute for lambda n that pattern that we saw before, 2L over n. And if you just rearrange this, you get that the frequency is equal to nv divided by 2L. Okay, v is the velocity in the waves, that's fixed. L is the length of the string that's allowed to vibrate, that's fixed. And n is just integers. 1, 2, 3, 4, and so on. Okay, and it's useful to think of this as kind of a sequence with a lowest frequency. The lowest frequency occurs for n equals 1, and that's going to equal, we'll call that f1. That's going to equal v over 2L. Okay, and that's often known as the fundamental frequency. Okay, that's the lowest frequency at which the string can vibrate. Okay, and you say, well, what about the other frequencies? What about fn? Well, fn is just going to be an integer multiple of f1. Okay, and so this is pretty simple. This is a pretty simple situation, and it's important physics, especially for people that are majoring in chemistry, because even though you know electrons in an atom, you think of them naively as like these little charged bundles that are orbiting the nucleus. That's not really the way electrons orbit. That's not the way electrons live inside of an atom. They actually form standing waves. And I know this is kind of a mind-blowing thing, but electrons at that level, you really should think of them as like little waves, okay, and not as particles. They act as both particles and waves, and this is the whole story of quantum mechanics. But just at the level of you know, the electrons inside of the wave, inside of an atom, they're acting like waves. And so this whole analysis of standing waves, when applied to atoms, explains why you get discrete lines in a spectrum. Okay, and so if you take a look at the spectrum of, say, something like helium, you know, like the helium signs that you see, those helium neon signs that you see that are glowing at different colors, you know, like kind of an orange and kind of a pink and so on, those discrete colors correspond to the discrete waves that the electrons are performing inside of the atom. And that's what those orbitals are about. Like you have the 1s orbital, and then you have the 2s orbital, and then you have the 2p orbitals, and so on. And they all correspond to different standing waves that the electron performs inside of the atoms. And so, just it's a bit of an aside, but just so you understand, like that this physics occurs in many different places. Also, obviously occurs in musical instruments because stringed instruments have waves which are tied down at both ends. Okay, and I'm not going to do this problem. We did it in class, but I do want to take a look at part B. It's very similar to the previous problem we just looked at with velocity of waves. And let's just take a look at part B. It says, what other frequencies can this string vibrate at? Well, I tell you in part A that the lowest frequency at which it can vibrate is 350 hertz. Okay, and so the fundamental frequency is 350 hertz. F1 is 350 hertz. That means the other frequencies are F2, which is 2 times 350, which is 700 hertz. F3, which is 3 times 350, which is 1050, and so on and so forth. So you can get all of the frequencies at which this string could vibrate at by simply multiplying the fundamental by an integer. Okay, so there's the story of standing waves. All right, skip that. Here's another phenomenon that waves can exhibit, and this one is most readily seen with sound, and it's known as beating, and it's a technique that's used for tuning a stringed instrument. Basically, if you have two waves which have similar but slightly different frequencies, okay, you get this really interesting phenomenon where you hear a note, but the note isn't steady in intensity. It goes loud, soft, loud, soft, loud, soft, like that, okay? And for Physics 112, you don't have to worry too much about the theory here. I'll just show you how to solve problems with this. But for Physics 102, this is another example of the superposition, okay? And superposition is simply the idea that if you have two solutions to your wave equation, here I have y1 and y2, and they're both cosines, and you can see one is a cosine omega 1t and the other one's a cosine omega 2t. They both have the same form, but the omegas are just slightly different, okay? And there's a trig identity which allows you to simply add the cosine of two angles. It's there at the top of the screen. Whoops, I'm in front of it. Let me move. Whoop, hold on here. Let me move myself down here. Okay, so you can see it there at the top of the screen. If you've got cosine theta plus cosine phi, there's an equation that allows you to combine those two in terms of two cosines that are multiplied together. Okay, I'm not going to expect you to memorize this trig identity, but there it is. And so when you add those two equations together, you're going to get two cosines, and the frequencies of these two cosines are actually very interesting, because the frequency of the first cosine here, look at what happened to the frequencies. It's omega 1 plus omega 2 divided by 2. And that's basically the average frequency, okay? So when you have these two notes, they don't have exactly the same frequency. You don't hear the two frequencies distinctly. They actually mix together, and you hear the middle of the two frequencies. So that's the note that you hear, okay? And that's the result of the first cosine. The second cosine, you can see there it's the difference between the two frequencies, omega 1 divided by omega 2 omega 1 minus omega 2 divided by 2, okay? And that's the difference between the two frequencies. That is the beating. That's the part that goes loud, soft, loud, soft, loud, soft. So basically you hear one note. The note is in the middle of the two original notes. The frequency is in the middle of the two original notes. But on top of that frequency, it goes loud, soft, loud, soft, loud, soft. Okay? And, if you want, you could probably just use YouTube and just look up beating notes, and there's a lot of examples of this phenomenon that you can experience. Okay, so there's one subtlety though about the beating here, okay, and here's what that subtlety is all about. All right, if you take a look at the actual waveform, in other words, if you were to plot that function that you just saw there, you would get that solid line. Okay, so here's the solid line here. Okay, and the solid line basically corresponds to the frequency that you would hear of the average of the two notes. It's 1/2 omega 1 plus omega 2. Okay, and then you would hear on top of that the dashed line. That's the loud, soft, loud, soft. Okay, and so you would have one beat, and then it would go quiet, and then there'd be another beat, and then it would go quiet again. Okay, now here's the subtlety. The two beats, the two neighboring beats, they are out of phase with one another. They're not necessarily in phase. Okay, and what does that mean? Well, probably the next diagram right here shows it a little bit better. Basically, all I did was I just isolated the two beats, and you could see that the one beat looks exactly like the other, but it's flipped. Okay, so whereas the one on the left has a crest in the middle, the one on the right has a trough in the middle. It's exactly, I tried to draw it as exactly the same form, but again, flipped 180 degrees. You can't hear that flip. Okay, you can't hear that phase shift. All right, and so as a result, the frequency that you hear, humans hear, is not a half of omega 1 minus omega 2. It's actually just omega 1 minus omega 2, okay? Because you simply cannot hear that phase shift, okay? Now, you say, well, why are we worried about that? Well, if you used an instrument like a pickup mic with an oscilloscope that you might do in a lab, and oscilloscopes are just devices that will pick out frequencies out of some kind of a signal, they're made to do that, you would see that the beat frequency that you hear and the beat frequency that the oscilloscope pick up, they're not necessarily the same. And so you might wonder what's going on. Well, here's what's going on. You know, the oscilloscope is noticing that phase flip between the two beats, but you are not able to hear that. Okay, and so so just keep that in mind when we do these problems. Okay, and so here's a problem. These are very easy problems. I'm not going to ask you to reproduce the theory. Okay, so here's a simple problem. Two strings emit frequencies 250 and 252 hertz each. Okay, so we got two sources, slightly different frequencies. What frequency do you hear, and what is the beat frequency? Well, you hear the average of the two, which is very simply a half of 250 and 252, which is 251 hertz. Okay, so that's what you would hear, but it wouldn't be a steady note of 251 hertz. It goes loud and soft, and the rate, the frequency at which that loud soft occurs, is simply the difference between the two. And we're using the absolute values because it doesn't matter which one's bigger than the other one. Okay, so basically it's just the difference between 250 and 250 hertz. So you would actually hear 2 beats per second. This note would be beating pretty fast, and so in 1 second you would hear this note go loud, soft twice. Okay, now if you instead were doing this in the lab, and you have this pickup mic and an oscilloscope, and you try to get the oscilloscope to detect that beat frequency, well, now it might notice this phase shift in there. Well, it would notice the phase shift in there, and you wouldn't get 2 hertz. You would actually get 1 hertz. You would that's what it would say to you. But you're hearing it, and you're going, no, I'm hearing 2 hertz, and you're wondering what's going on. Well, that's what's going on. Okay, so that's just a an important thing to distinguish, because humans can't hear that phase shift. Your beat is actually going to be, in this case, 2 hertz. Okay, so this is yet another phenomena that waves undergo. All right, and for the next set of phenomena, we're going to study 4 more phenomena in this lecture. We're going to expand our world and not just consider one-dimensional waves, which are waves like are on a string, but you can expand this to 2- and 3-dimensional waves. And for Physics 102, that wave equation I gave you was really just a one-dimensional wave. It was y as a function of x and t. Okay, but it was just x, and that's one dimension. But you could have 2 dimensions, 3 dimensions, and so on. And waves will travel in multiple dimensions. So an example of a wave in 2 dimensions, like waves on the top of water. Okay, so if you've got like a bathtub full of water, and you just bob your finger up and down on your bathtub, and you see those waves that travel along the surface, those are 2-dimensional waves, because the water air interface is 2 dimensions. But you could also have 3-dimensional waves, and that's the example of sound. Okay, so with sound, you could picture the crest is kind of like a sphere, and that entire sphere will grow over time. Okay, and so you could have 2-dimensional and 3-dimensional waves. Now it gets a little hard to try to draw wave phenomena. I'm not going to prove any of these phenomena directly from the wave equation. I'm just going to tell you phenomenologically how they how they unfold. But it's kind of hard even to just draw these wave crests traveling in multiple dimensions. So rather than that, it's we define this thing called array. Okay, an array is a much easier concept to draw and an easier concept to get your head around. So what I've drawn here is basically maybe you can picture this as looking down on the surface of water, and you have a series of crests and troughs. So those vertical lines that you're seeing, the solid lines are crests, the dashed lines are the troughs between the crests, and this set of crests and troughs, they're moving to the right of the screen at some constant velocity. Okay, and so rather than trying to draw this mess of crests and troughs, I'm going to reduce that all to just one line, a ray. Okay, and the ray is basically perpendicular. It's drawn perpendicular to the crest fronts, and it points in the direction of the propagation of the wave. Okay, and so in the diagrams that you're going to see next, I'm not going to try to draw the crests and troughs. Rather, I'm just going to draw the direction in which they're moving. In other words, the ray. Okay, so what phenomena are we going to look at? Well, there's 4 phenomena, and they are reflection. That one's easy. Refraction, diffraction, and interference. Okay, so these are all wave phenomena that they'll happen in 1D, but to really appreciate what's going on, you need to look at them in multiple dimensions. And so we're going to consider them in 2 and 3 dimensions. Okay, so let's start off with reflection. It's absolutely trivial. And we'll also compare these phenomena to their equivalent phenomena if we had particles. Okay, so with reflection, basically, if you follow the ray of a wave as it impinges with a surface which is like a mirror, a specular surface, all you get is that the incident angle of the ray is equal to the reflected angle of the ray. Okay, and to make that more precise, what you're seeing there in the diagram is you see this base here, and this base right in here, that's your mirror. Okay, and then you have an incoming ray, and it impinges with the mirror, and then it bounces and it goes out. Okay, the dashed line, which is perpendicular to the mirror surface, that's known as a normal. Okay, and you measure the angle of the incident ray to the normal, and you measure the angle of the reflected ray to the normal, and you go, is there a relationship between the two? And the answer is yes, they're just equal to one another. That's it. There's nothing more to say about that. It's not exactly like I can ask some very deep questions about this. You just need to recognize that the rays, the incident angle of the rays is equal to the reflected angle of the rays. Okay, how does that compare with particles? Particles do the same. Okay, with particles, you would get this out of like conservation of momentum. All right, and so conservation of momentum would have that the incident angle is equal to the reflected angle, but guess what? Waves do the exact same thing when you follow their rays. All right, so let's move on to the next phenomenon, which is refraction. And what's refraction? So refraction is basically the bending of the rays when they pass from one medium to another medium. Okay, so the classic example here is light traveling from air to water, but it can happen with anything. It could happen with sound traveling from from like air into like the walls and then out again into air. Okay, so you know how sound can travel through walls. Okay, what's happening there is basically the air waves, the sound waves will travel through the air first, and then they'll travel as sound through a solid, and then they'll come out again. So this doesn't just happen with light, but like I said, the classic example is light, and it's air and water, because everyone who's gone swimming knows this. You know that things look kind of squished when they're in the water, and that's because of the bending of the rays. And so what you're seeing in the diagram there is you're seeing a ray which is coming from the air. Okay, you can see the arrow there is pointing from the air, and then it meets the interface between air and water. Okay, and it bends. Okay, it bends towards the normal in the water. All right, and the bending is determined by this quantity called n, which is the index refraction. It's basically just a property of the material. And a proper analysis of this shows that the index of refraction is inversely proportional to the speed of the waves in each material. Okay, so in a given material, the velocity of the waves doesn't change. All right, we stated that already. But if you got two different materials, that doesn't mean that the velocities in these two materials are going to be the same. Okay, so when you go from one material air to another material water, the speed of the waves does change. Okay, and that changing of the speed of the waves causes them to refract. All right, and this is governed by a formula known as Snell's law. All right. And what does Snell's law say? So here I just used 1 and 2, subscripts 1 and 2 to refer to any old materials, material 1 and material 2. But basically it says, look, if you calculate N1 sine theta 1, and N1 is the index of refraction in material 1, and sine theta 1 is the angle that the ray makes in material 1, that's got to equal N2 sine theta 2 for material 2. Okay? And it's a fairly simple formula, and well, let's use it to look at how light bends when it travels from air to water and then also from water to air. So we did these examples in class, but this is a bit of a review, and so let's do it again. It's worth doing these again. So here we go. We have a ray which travels from air, and air has an index of refraction, which we will call Na equal to 1. That travels into water, and water has an index of refraction, NW equals 1.33. Obviously, I don't expect you to memorize these numbers. I would give them to you on a test, okay? There's the index of refractions for air and water. The ray makes a 45-degree angle to the normal in the air. Okay, so you can see it there in the diagram. This air is, the ray is coming in the air, and it impinges on the water, and it impinges in such a way that it makes a 45-degree angle. Okay, and the question is, what is the angle in the water? And whenever you're traveling from a material with a low n to a material with a higher n, the ray always bends towards the normal. Okay, so let me say that again. So if you travel from a region where n is small, like that's the air, to a region where n is big, that's the water, the ray will bend towards the normal in the material of the bigger n. Okay, so you can see that the ray is, theta w is going to be smaller than 45 degrees. Okay, you can see that from the diagram. All right, but we can actually calculate it exactly using Snell's law. So over here, here's Snell's law. I replaced again the subscripts with A and W because we know the materials are air and water. So the index of refraction for air, 1. The angle that the ray makes with the normal in air, 45 degrees. The index of refraction for water, 1.33. And the only unknown is theta w, so we solve for that. Now, we get to this point where we have sine of theta w is equal to 0.532. And you go, how do I solve that? Well, this is similar to when we had the tangent and the inverse tangent when we were doing the conversions between Cartesian and polar. Okay, basically you have to take the inverse tangent, and so the angle is going to be equal to the inverse tangent of 0.532, and that turns out to be 32.1 degrees. Okay, so make sure you know how to do that on your calculator. Every calculator is slightly different. It's usually like you have to press the button's inverse sine, or you might have to press the button second sine or whatever. But you've been doing this with the tangent. It's just the same thing, but now with the sine. Okay, so part B. Let's reverse the situation. This time, the ray is going to make a 45-degree angle to the normal in the water, and then it refracts out into the air. Now, because the air has the smaller end, this time the ray is going to bend away from the normal. And so you can see here from the diagram that theta A is actually going to be bigger than 45 degrees. And let's calculate it. All right. So here's Snell's law. We substitute in for Na, 1. We substitute in for Nw, 1.33. We substitute in for theta W, 45 degrees. The only unknown is theta A. We solve for theta A, and we get 70.1 degrees. Okay, and sure enough, 70.1 degrees is bigger than the 45 degrees. And so you get the bending away from the normal in the material of smaller n. All right. Now, this leads to an interesting situation, okay? And the situation is this. If I keep making that 45 degree bigger and bigger and bigger, then theta A is going to get bigger and bigger and bigger. But theta A is going to get bigger faster than the 45 degrees is going to get bigger, okay? The angle of the water is going to get bigger, all right? And so there's this critical angle in the water. such that once you get to this critical angle in the water, it's around 48 degrees, we'll calculate that in a minute, the angle in the air turns out to be 90 degrees, okay? And if you go past that critical angle, you might ask the question, well, then what's the refracted angle? Because can you have a refraction bigger than 90 degrees? The answer is no. Once you get to this critical angle, this is the maximum angle in the water at which refraction occurs. If you go past that angle, the refraction stops and it turns over to reflection. And what that basically means is that the interface between the air and the water at angles bigger than this critical angle, it just looks like a mirror. It just turns into a mirror and it purely reflects. Okay, so let's take a look at that critical angle for the interface between water and air. All right, and so here's part C of my problem. What is the critical angle for rays traveling from water to air? And you can see in my diagram, the ray is making an angle in the water, and I called it theta r for theta critical, okay? And in the air, it's refracted, and the angle is refracted at 90 degrees, okay? And that's as far as you can go, all right? So now what? Well, how does that work? Well, let's take a look at Snell's law, okay? And I kind of squeezed it here into the bottom. Hold on here. Okay. So let's take a look at Snell's law. I have, again, the index of refraction for air is 1. The angle now in the air, there's your maximum, 90 degrees, okay? And the index of refraction for water, that's NW, okay? And we don't know the angle in the water, but it's going to be that critical angle, okay? Now, sine of 90 degrees, that's as big as you're going to get. That's 1. Okay, so if you solve now for theta r, it turns out to be 48.6 degrees. So there's that critical angle. So now, what does this mean? This means that for angles that are smaller than 48.6, you're still going to get the refraction that we've been discussing up to now. But if your angle, that is the angle that the ray makes with the normal, is bigger than 48.6, you're going to get reflection, okay? And the water-air interface basically starts to act like a mirror, okay? And so this is the story of total internal reflection. You're only going to see the total internal reflection when you go from the water to the air, never from the air to the water, okay? And that's because total internal reflection only occurs when you go from big N to small n, not vice versa, okay? By the way, an example where you might have seen this phenomenon is a mirage. So you know that on a hot day, you look at a road, okay, and you see that up along the road, it looks like there's water on the road, but really it's kind of a shimmering silvery. And what that is basically the air at the top of the road is hotter than the air above it, and so the air, just the layer of air just above the road has a smaller air than the air above it. So you're in the air of bigger N, and the air on the surface of the road is smaller N, and so the light reflects off of it and it acts like a mirror, and so you get this mirage. So there's another example. This is probably a more common example of an experience of total internal reflection rather than water, although it's not obvious with the mirage. But if you ever go down in a pool and you look at angles that are bigger than that 48-degree critical angle, you'll definitely know what I'm talking about, because the water will just the air will just look like a mirror, okay? And so there it is. There's the story with refraction. Okay, next phenomenon is diffraction. Okay, so diffraction is a very interesting phenomenon because it's one phenomenon that definitely distinguishes particles from waves. Okay, so particles reflect just like waves reflect. Particles will actually refract just like waves refract, and Newton actually discussed this in his book on optics, because he thought that light was made out of particles. But I don't want to go into that study. It's not that interesting. But yeah, particles will refract just like waves will refract, but only waves will exhibit diffraction. Okay, so what is this diffraction? It's basically this phenomenon where waves will bend themselves around a barrier. Okay, so let's start off with the example of particles. And you can see here on the left-hand side of the screen, I've got a set of particles, and I'm firing them at a screen, which is at the right-hand side of the screen, okay? But between the particles and the screen is a barrier, okay? And particles which are fired at the screen that don't encounter the barrier, well, they just continue straight. They get to the screen and they boop, hit the screen and make a little impact point. So you can see all those little black dots there that I indicated on the screen. They're supposed to be the impact points of all the particles that have hit the screen, okay? And so here's a second particle, below it is a second particle, then a third particle. Any particles that hit the screen, that hit the barrier, they don't make it to the screen. And particles that miss the screen, miss the barrier, make it to the screen. So what winds up happening on the screen is you're going to see a sharp shadow between that region where particles do impact the screen and that region where particles do not impact the screen, okay? A very sharp shadow. So how is this different than waves? Well, here, if we follow some wave crests as they approach a barrier, okay, when the wave crests get to the barrier, yeah, the barrier will clip the wave crests, but guess what? The wave crests on the other side, they start to bend, okay? So I've got that dashed line in there, and this dashed line in here indicates kind of like the limit of the bending. Okay, so the waves that don't meet the barrier at all, the crests that don't meet the barrier, well, there's still these straight crests and they'll continue forward, okay, onto the screen. But then at the edge of those, there'll be kind of like a semicircular uh, piece of the crest, and that's the part of the crest that's diffracted or bent around the corner. Okay, so the circular part of the crest on the right hand side of the barrier are the diffracted part of the wave. Okay, now what would you see on the screen? You wouldn't see a sharp shadow. Instead, you would see above the barrier, okay, you would see definitely bright. All right, I'm thinking of light here because this experiment is easily done with light and like with a laser and a razor blade. So basically you would see this very bright region. Okay, and then in the region where you have the diffracted wave, it would start off bright and then it would slowly start to fade as you move away from the bright region. It would slowly start to fade to black. Okay, and then finally, when you're far away from the diffracted area, okay, so even so far that the wavelets just can't diffract that far, basically the screen would be black. Okay, and so you don't see a sharp shadow, rather you see a kind of a slow smearing from bright and fading to black or dark. All right, and so no sharp shadow, waves. Sharp shadow, you have particles. Okay, how would you do this with a laser and a razor blade? Very simple. You know that you've got a laser beam and you shine that on the wall, and it would be this very bright dot. You take the razor and you bring it up to the laser beam, and so it's just impinging on the laser beam, and you'll see that spot on the wall gets smeared out. And you say, well, why is it being smeared out? That's that fade from bright to dark. Okay, and so that smearing that you would see because of the edge of the razor blade impinging on the laser beam, that's basically your diffraction, and you would see this kind of a fading from the bright dot, and then there'd be a smear, and then eventually it would fade out. Okay, so again, this is a phenomenon that only waves will exhibit. All right, and there's a couple of interesting situations with diffraction. One of them is where you have a barrier, like in this situation right here. Okay, and so here you have a barrier, and you'll as the crests go around the barrier, they'll diffract on either side, and so you'll get this triangular region right on the far side of the barrier, which the waves don't quite penetrate, and that's the dashed lines in there. But they are diffracting, and you've got this kind of these circular wavelets that are that have bent around the corner, and eventually they'll meet up. Okay, the waves that diffracted on one side will meet up with the crest that diffracted on one side will meet up with the crest that diffracted on the other side. They'll meet up and they'll kind of heal on the other side. You'll still have this little dimple, this kind of a memory that they went around the barrier. Okay, there'll be a little dimple there, but the waves will kind of heal and then they'll continue on. Okay, so the barrier does not exhibit any kind of a sharp shadow, and the waves will just eventually bend right around it. Okay, the same thing happens with a hole, but now the bending is in the opposite direction. Basically what you get here is you have a hole, and then the waves will bend around on either side, and this leads to this kind of circular wavelets that come out on the other side. Okay, so the crests expand as they exit the hole. All right, and again, this is a very easy experiment to do with laser. You just simply take some barrier, some like a sheet of paper, and you put an ever tiny hole. Okay, the smaller the hole, the better. Maybe something that you could use like the head of a pin or something like that. And then you let the laser beam hit the hole, and you would see that on the other side, the sharp dot gets smeared out. Okay, now the smearing out actually has a bit of this interference, which we're going to talk about next. But that's definitely there'll be a smearing out of the waves as they exit through the hole. Okay, so this is diffraction. I'm not going to give you a formula for it, but there is something important about the size of the hole. Okay, so diffraction is not very evident. You're not going to really see this phenomenon in diffraction unless the hole or that barrier that you just saw a minute ago in those diagrams, unless the hole and the barrier are approximately the size of the wavelength, you're not going to get any kind of appreciable diffraction. Okay, so if the wave is much larger than the hole, then basically the wave is just not going to get through the hole at all. Okay, there'll be no amount of wave that will exit it, and so the wave is basically, even though there's a hole there, it just the wave experiences that barrier as just a solid barrier. Okay, it doesn't see the hole. And there's an interesting application of this, and that's the door of a microwave oven. If you take a look at the door of a microwave oven, you'll see that it's a metal screen. Well, there's the plastic there, but embedded inside the plastic is a metal screen, and the metal screen has tiny little holes in it. You'll see these tiny little holes. And the tiny holes are about a millimeter in size or so. I haven't measured them, but they seem to be about a millimeter. But a millimeter is much smaller than the wavelength of microwaves, which is about 5 centimeters. Okay, and so the wavelength of the microwaves inside the microwave oven are about 5 centimeters, and the holes are a millimeter. There's no way that the microwaves can make it through those holes. All right, but you can see inside. Okay, now microwaves and visible light, they're both in the same family of waves. They're both electromagnetic waves. The light can make it through, and that's because light has a wavelength of about 550 nanometers. Okay, and that's somewhere in the green region. All right, and nano means 10 to the minus 9. We'll actually make use of that in just a second. So the light, because it has a wavelength which is much smaller than the holes, it gets through no problem. And in fact, it's much smaller than the holes, so that there's no diffraction. You don't see things inside the microwave blurry. Okay, they're not. The image isn't blurred out because the shadows have been blurred out because of diffraction. No. The wavelength of the light is much smaller than the hole, and so there's hardly any diffraction effect at all. Okay, and so that's how a microwave oven allows you to look inside but not actually get burnt from the microwaves that are in there. Okay, so that's the story with diffraction. The last phenomenon that we're going to study is interference. And interference, like all of these phenomena, they go back to that wave equation, which we studied in some detail in Physics 102. And they all go back and they all have something to do with this superposition, which again we studied in 102. But it wasn't obvious for the previous ones. It's kind of very subtle. It requires, some fairly sophisticated mathematics. But when it comes to interference, it's pretty obvious how this superposition comes into play. And superposition just means that if you have two sources of waves, and the two sources of waves, they produce waves and the waves meet, what happens? And the answer is they just add. Okay, they just add. And so that's what I'm trying to indicate with these diagrams that you're seeing here. Okay, you can be in a situation where in a particular region of space, all right, one source of the waves is trying to put a crest there, and the other source is also trying to put a crest at the same region of space at the same time. And so what winds up happening is the two crests add together, and you get a bigger crest. Okay, so they're additive. Similarly, you can be in a region of space where one source is trying to put a trough there, and the other source is also trying to put a trough there at the same time. And so you've got a situation where a trough is meeting a trough. And what do you get? Well, they add. You can think of the troughs as being negative, so you get an extra negative. You get a bigger trough, okay? And so whenever crest means crest, you get a big crest. Whenever trough means trough, you get a big trough. We call that constructive interference because the crests are helping one another out, or the troughs are helping one another out. This is to be distinguished with other regions of space where one source is trying to put a crest there while the other source is trying to put a trough. Okay, so if you're in a region of space where at a particular time a crest from one wave is meeting a trough from the other wave, they cancel. They cancel. You can think of the crest as being positive and the trough as being negative, and you add a negative and a negative and a positive, they cancel. And so those regions of space are called regions of destructive interference. Okay, and so leads to a very interesting phenomenon. All right, so what happens? Well, try to show that over here. It actually happens for both single slit and double slit. We'll study each one of them in turn, but let's look at the double slit first. So in this diagram, what you're looking at is a barrier, and there are two holes there, okay? I've got hole number 1 marked as number 1. I forgot to mark number 2. I don't know why, but the hole on the top here, this is hole number 1, so that's source number 1, and here's hole number 2 right below it, okay? Now, remember what happens to waves when they travel through a hole. They will diffract, and so they'll form these kind of circular wavelets on the other side, okay? I didn't even bother trying to show what the waves look like on the left-hand side, which concentrate on the right-hand side. So one hole is creating these circular wavelets, and the other hole is also creating these circular wavelets, and so you have two sources of waves, and they're meeting one another. And so what I've drawn there are just the crests from number 1 and the crests from number 2. Those solid circular lines are just crests from number 1 and crests from number 2. So here's a crest from number 1, here's a crest from number 2. Look at in the middle there, they're meeting. So I circled that place where they meet, where they cross one another, and that region is a region where a crest is meeting a crest, okay? And you get constructive interference. It turns out that if you wait a little bit, at that very point, a trough from number 1 will be meeting a trough from number 2, and so you'll still get constructive interference. So that region with a circle is a region where you'll always have constructive interference. Okay, always have constructive interference. Now, right beside those regions of constructive interference, you're in another region where, because of the slight difference in the path lengths, the crest from one source is always going to meet a trough from the other one, and vice versa. And so what you wind up getting, if you do a full analysis of this, is you get these kind of regions where you're always going to have at all times, you get constructive interference in the middle, and then that's bordered by destructive, and then those are bordered by constructive, and then destructive and constructive, all the way out until you get to 90 degrees, okay? And obviously you can't go further than that, okay? So that's kind of interesting that you get this pattern, and this pattern persists in time, okay? In other words, the middle is always constructive. It's not like it's constructive and then at a later time it's destructive. It's always constructive interference. And constructive interference, where crests are adding to crests and troughs are adding to troughs, this, if you're talking about light, that's bright, okay? Or if you're talking about sound, that is loud. Those are regions of loud, okay? The destructive interference, that's where crests and troughs are canceling one another out. If you're talking about light, that's dark. Those are regions of dark. Or if you're talking about sound, those are regions of quiet. Okay, so the two holes there, you could think of them as like two slits in a barrier, and you're shining a laser beam through them. But I once did this with two speakers. Okay, so where the two holes are, you can imagine two speakers, and I had them on a sound generator, and they were in phase. It's very difficult to do because sound bounces off of all the walls and everything like that. But I had it all set up just right in a lab many years ago, and I walked around it, and you could tell when you were in one region, it sounded like the speakers were loud, and when you walked to another region, you could barely hear them, and then you walked to the next region over, they were loud again. And so it was interesting, as you walked in front of these pairs of speakers that were a certain distance apart, you would go from loud, soft, loud, soft, loud, soft, and so on. Okay, so this is a phenomenon which is very particular to waves. Again, particles just do not do this at all. Okay, so this is it was actually, the double slit experiment was actually developed by a physicist called Young, and he used it to prove that light was actually a wave phenomenon. Okay, this confused people, and they kind of ignored him because Newton had years earlier said that in his book Optics, it said, well, no, light is made out of these corpuscles, these particles, but it turns out that Newton was kind of like incomplete. He was wrong. Light acts more like a wave than it does like particles, although we don't want to get into the quantum mechanics of the wave-particle duality. But no, if you do this with like a laser beam, and I'll show you this a picture that Dr. DeHaven has in his book, you could definitely see the light-dark regions. Okay, let's do the math first, and then I'll show you the a picture of of this being done with the laser. So here we have the two slits. I didn't even bother trying to draw the wavelets or anything like that. I simply drew the barrier, and you'll see the barrier has two holes, and the distance between the two holes is D. Okay, so the distance between the two holes is D. If you go straight along the middle, that's theta equals 0, you're going to hit a bright spot. Okay, so on the screen at the very middle of the two holes, that's a bright region, and we're going to call that region M equals 0. Every time you have a double slit experiment, the very middle is bright, and we can call that M equals 0. Well, on either sides of the bright band are two dark bands, okay? And so there's a dark band on top of that. We'll call that M is equal to a half, and there'll be a dark band below it, and that's as M is equal to negative a half, okay? Then beyond the dark bands, you're going to have more bright bands, okay? And that next bright band is going to be M equals 1, all right? So the convention we're going to use is that bright bands are going to be M is equal to 0, 1, 2, 3, and so on, integers. And the negatives are going to be allowed too because it's symmetrical around M equals 0. So you could say M is equal to 0, M is equal to plus or minus 1, M is equal to plus or minus 2. That corresponds to bright. And for the darks, they're going to be the half integers, a half, plus or minus a half, plus or minus 3 halves, plus or minus 5 halves, and so on, okay? Now, if you're looking at a particular band, say in my diagram here, I'm looking at the bright band M equals 1, I can ask the question, at what angle does that bright band occur? That's theta. And there's a formula for that, and here it is, okay? The angle at which the bright bands occurs is given by D. That's the distance between the two holes. The size of the holes doesn't matter that much, except insofar as they have to be at least around the size of the wavelength because of diffraction. Otherwise, the waves won't diffract through them. But the exact size of the holes is not relevant, okay? It's the distance between the two holes, D, multiplied by sine theta. That's the angle at which you're looking to see whether you've got a bright or dark band or whatever. That's going to equal M, which is one of these integers, times lambda. Okay, so d sine theta is equal to m lambda, where m is equal to 0, 1, 2, 3, or the negative integers are allowed as well. Okay, so that formula with m equals to an integer, it tells you where the bright bands are, the angle of the bright bands. The same formula will also tell you where the dark bands are, but this time you can't use an integer in m, you have to use one of the half integers. So m is equal to either plus or minus a half, plus or minus 3 halves, plus or minus 5 halves, and so on. So whenever you have one of these half integers, then you're going to get the angle of the dark bands. Okay? So there's the story with double slit, and we're going to do a problem with this, but let's get the situation with single slit out of the way. When you have a single slit and you get the diffraction going through there, you get a similar pattern, but you might wonder why. Where are the two sources? It's actually not two sources. It's actually infinitely many sources. And you wonder what's going on there. Well, it turns out that every single wave, every single point along the crest that passes through the hole acts like a source, acts like a new source. And so unlike the double slit where you have two sources, in the single slit, every point along that hole acts like a new source. You've got an infinity of sources there, okay? Now, you might wonder, well, what's going on there? Like, why does it work that way? Well, this was kind of Huygens' principle, and Huygens was this Dutch physicist, and he realized that every point on a crest acts like a new source for the next generation of waves, okay? And because of the principle of superposition, that is the adding, you get that the wavefront propagates. But when you get to this hole, you can think of it as having infinitely many sources, and then all those infinitely many sources, they'll interfere with one another. Okay, so you're getting an interference pattern which is based on the interference of all the points along the stretch of the hole. Needless to say, this is a fairly complicated situation. You could do a sort of a simple analysis, but a proper analysis, like anything else, requires calculus. Anytime you hear adding up like infinitely many whatevers in physics, you know you're talking about integration or some kind of calculus, okay? So we're not going to do that, but I can at least show you what the result is going to be, and the result is this, okay? Basically, you have a hole in the barrier, and now the hole has a width A associated with it. The size of the hole does matter now. So that's A. And on the screen, at angle theta equals 0, you get this really big central bright band, okay? Super big, okay? And that's the central one. On either side of the bright central band, you have two dark bands, okay? And we're going to call those n equals 1 and n equals minus 1. Then you have two bright lines, bright bands on either side of those. And then we have darks beyond those, and those are going to be like n equals 2 and n is equal minus 2, and so on and so forth until you get to 90 degrees, and you can't have any more than that, okay? And so for this particular situation, the angle of the bright bands, it's not symmetrical, and so the angle of the bright bands is a very complicated formula, but at least we can say where the dark bands are going to occur, okay? And the formula for just the dark bands looks the same. It looks like this, but there's a few differences. First, it's A and not D. D above was the distance between the two holes, but we don't have two holes here. It's A. It's simply the width of the hole. Okay, and N, being an integer, above I called it M on purpose, okay, to distinguish it for N. An integer N here for a single slit corresponds to a dark band, not a light band, okay? This causes confusion, as you might imagine, because the two formulas look the same, and in one case, the integers correspond to bright, that's for a double slit, and in the other case, integers correspond to dark, that's a single slit, and so you can easily get confused, so just make sure that you think about this very carefully and memorize it correctly, okay? So there's the formula for the dark bands, and again, n can be negative or plus or minus 1, plus or minus 2, and so on. And the plus or minus is because it is symmetrical around the middle bright band, and the middle bright band is very bright, okay? Most of the energy goes there, but there is these kind of fringes of light, dark, around that very bright middle band, okay? So there's the theory. Let's do a problem, and then I'll show you a few pictures out of Dr. DeHaven's textbook. Okay, so here's an example. Part A, the wavelength of blue light is 450 nanometers, and remember, nano is 10 to the minus 9. We pass it through a single slit of width 1.5 micrometers, and micro is 10 to the minus 6. At what angles do the dark bands occur? Okay. What angles do the dark bands occur? So there's going to be several of them, but we're just going to calculate a few of them, okay? And then part B says repeat this, but this time assume that there are two slits, and the two slits have a distance of 1.5 micrometers apart from each other, okay? At what angles do the dark bands occur, and at what angles do the light bands occur? All right, so let's do the single slit first, part A. And in part A, we're going to use the formula A sine theta is equal to n lambda, okay? Where, again, we're just looking for the dark bands now. Now, A is equal to 1.5 micrometers, and micro is 10 to the minus 6. I've got that written here on the side, okay? And so that's equal to 1.5 times 10 to the minus 6. Lambda is 450 nanometers, and that's 450 times 10 to the minus 9, which I could write as 0.45 times 10 to the minus 6 meters. And the reason I converted it from 10 to the minus 9 to 10 to the minus 6 is so that they'll cancel out. So if you take a look at the next line, I rearranged the formula. Sine theta is equal to n over lambda divided by a. Now I can simply do lambda divided by a. That turns out to equal 0.03. Okay, and so my formula is sine theta is equal to n times 0.03. And again, when I substitute different values of n, integer n's, I'll get the different angles at which the dark bands occur. Okay, so the first dark band is going to occur at n equals 1. So if I put 1 in there, I'm going to get sine theta is equal to 0.3. So theta is going to equal the inverse sine of 0.3, which is 17.5 degrees. Okay, and again, it's going to be 17.5 degrees on both sides. That's why you have n is equal to plus or minus 1. All right. We'll just do one of them because we know that symmetry is there. Okay, so for n is equal to 2, so now we substitute n equals 2 in there, and so we have sine of theta is equal to 2 times 0.3, which is 0.6. So theta is the inverse sine of 0.6, which is 36.9 degrees. And so on. You can do more, like at n equals 3, you get 64.2 degrees. Obviously, n can't go on forever because as n gets bigger and bigger and bigger, you start to approach 90 degrees, and it just doesn't make sense because, you're not going to have a screen that's going to go past 90 degrees. That's like on the other side of the barrier, so that doesn't make any sense. Okay, so we got three angles there, and I probably could squeeze out a fourth, but I didn't do that. And don't forget, these, for the single slit, these are the angles for the dark bands. All right, so the angles for the dark bands here. Okay, now if we did the double slit, we would have the same formula. All right, but now for the bright bands, you have integers, and for the dark bands, you have the half integers. All right, so if we rearrange the formula, all right, we get that sine theta is equal to m times 0.3. It's 0.3 again because lambda is the same, and instead of a equals the 1.5 micrometers, here I had d is equal to 1.5 micrometers. Okay, so the ratio lambda over a and lambda over d are the same, 0.3. Okay, and let's look at the bright bands first. For m equals 0, that's the central bright band in double slit interference, theta is equal to 0. That always happens. There's always a bright band in the very middle for double slit interference. Okay, for m equals 1, I didn't even bother plugging in because the math looks identical to part A. You get that theta is equal to 17.5, and that's going to be for the first bright band. And then for m equals 2, you're going to get 36.9, and that's for the second bright band, and so on. Okay, so what was dark for part A, dark bands for part A, is actually the bright bands for part B. Okay, so try not to get confused there. Again, part A was a single slit, part B is a double slit. Okay, but let's take a look now at the dark bands. Okay, for the dark bands, same formula, but this time we use the half integers: a half, 3 halves, 5 halves, and so on. So if we solve, but this time we substitute n is equal to a half, or sorry, m is equal to a half, I get that sine theta is a half of 0.3. So theta is equal to the inverse sine of 0.15, which is 8.6 degrees. Okay, so the dark bands occur on either side of the central bright band at 8.6 degrees. The next set will occur at 26 degrees because that's m is equal to 3 halves. And then the last one occurs, the m is equal to 5 halves, that occurs at 48.9 degrees. Again, there might be more, but I did 3 of them. Okay, and so there you go. There's the story with double slit interference. Okay, so part A was single slit interference and part B is double slit interference. All right, so let's close off this lecture, but before I do, let me just show you some pictures. This is a very busy picture and it's very hard to do, but this is basically your double slit interference, and you can see here that there are two sources. They correspond to the blue and the red dot in the diagram, and so the blue dot produces blue wavelets, which you can see, as these circles centered around the blue dot, and the red dot produces red wavelets, these circles that are centered on the white dot. And the purple lines, you say, what are they? They are lines in which a crest from blue meets a crest from red. Okay, and so those purple lines are lines of always constructive interference. Okay, and you can see the kind of pattern that they're forming. In between those purple lines are regions of always destructive interference, and that's why in double slit interference you always get this bright dark pattern. Okay, and it's very easy to do this in an experiment. And so here's a picture of taking a laser and passing it through double slit, and you can see, da-da, bright dark. And so on top you have red, in the middle you have green, and then after that you have blue. You'll notice that the sizes of the dots for the red are bigger than the green, and the green are bigger than the blue. And the reason for that is that the wavelength for red is bigger than the wavelength for green, which is bigger than the wavelength for blue. Okay, and so yeah, the pattern does depend on lambda. If you go back to the formula, you can see that there was a lambda in it. So the bigger lambda is, the bigger the angles are at which the bright dark bands occur. Okay, very simple experiment to do. Unfortunately, if we were in the lab, I would have probably pulled out a diffraction grating, and you could just simply use one of those pointer lasers. Any laser will do, and you shine it through there, and what you get is you just see that pattern. You go, well, what's causing this pattern? Why is this pattern like that? If you've got two slits, why don't I just see two holes? That's what you would see if you had particles. That's because light is not acting like a particle there, it's acting like a wave. And the wave is interfering with itself. The two sources coming through the two holes are interfering with itself, forming the interference pattern, which is characteristic of waves. Okay, guys, this ends this lecture on waves. The next lecture is going to be on sound.